Alright, so I did this video already, but my phone ran out of space and lost everything, so that file's gone. So instead of erasing this all, rewriting everything and explaining everything, I'm just going to real quickly go over everything that I did in the last video. And because it's already written out, I'll go through it a lot more quickly. So anyways, what we did is we basically just proved a proposition. And so if you have G as a group and N is some normal subgroup of G, then G is solvable if and only if both N and G mod N are solvable. And so it's an if and only if, so you just do both directions separately. For the forward direction, suppose G is solvable, which means that d to the n g equals e for some n greater than or equal to 0. Well, if it's n equals 0, then it's trivial, and so that's trivial. But that's not an interesting case. So anyways, what you have is you have dn of n is contained in dng, which is equal to e. So this inclusion, that's what I have boxed down here. This is an induction argument. It's kind of trivial. Well, it is trivial when n equals 0, because what you have is it just says dn is just the group generated by elements of the form n1, n2, n1 inverse, n2 inverse, where n1 and n2 are in n. But then this obviously, since n is contained in G, this is contained in the group generated by elements of the form G1, G2, G1 inverse, G2 inverse, where G is anything in G. And this, of course, is the commutator of G. Okay, so that takes care of the base case for this inclusion. But now if we induct and suppose that it holds up to, say, let's see here, this is a fixed n here, so let's say m. So d of, suppose that d to the m of n is contained in d to the m of g. Then if you take the then basically you can just raise this to the power of m and put the d there, and it's the same argument, because now we just suppose that n1 and n2 are elements of dmn, and suppose that g1 and g2 are elements of dmg. And then this inclusion holds because of the inductive hypothesis, which is that dmn is contained in dmg, and therefore we get d to the m plus 1n is contained in d to the m plus 1g, and that completes this induction argument. Okay? So that's, obviously this thing is trivial because we chose n such, and so then n is solvable. Okay, then you let pi be projection onto g mod n, and then what happens when you project the commutator? What you get is you were projecting this, and so that's projecting the group generated by elements of this form. But if you take the projection of any element of this form, it's going to look like this. And of course, if you look at the group generated by elements that look like this, what you can write this product as an, bn, a inverse n, b inverse n, that product being taken in g mod n, which is the projection of g. And so this is precisely the commutator of the projection of G, i.e. it's the commutator of G mod n. So if you apply D to G mod n, you get pi of dg. If you apply it again, then you're going to get pi of d of g. So if you have d to the 2 g mod n, that's going to be equal to pi of d to the 2g. And so if you just apply it n times, you're going to get d to the n of g mod n is the projection of d to the ng, which is the projection of, well, d to the ng, that's just e. And so we have this projection of just the identity element, but you project the identity element, that just gives you n. And that's, of course, the identity element in g mod n. So thus, g mod n is solvable. Okay, so that takes care of that direction. For the other direction, you suppose that you have a normal subgroup n such that n and g mod n are solvable. And we proved last time that being solvable is equivalent to having a composition series with abelian graded pieces. And so let's let sigma be a composition series for n with abelian graded pieces, and sigma bar is a composition series for G mod n with abelian graded pieces. Now here, the reason, note that I'm writing this as G naught mod n contains all the way down to Gm mod n, which is E. The reason that we know that these subgroups look like this, so here the GIs, G naught, G1, Gm, these are all subgroups of G. And we know that because of the first isomorphism theorem, which tells us that all subgroups of the quotient group are of this form. So anyways, what you do is you let Gj be the inverse projection of the Gj mod n of this particular coset. So what we're doing is we're just taking this and we're taking sigma bar and we're just pulling it back. So let's see here. The inverse projection of Gm, well, that's just the inverse projection of the identity, and so that's just n. The other thing to note is that what we're doing is we're taking each of these inclusions here is normal, and we're pulling that back through a group homomorphism. And we proved in a previous video that pulling back things through group homomorphisms preserves normality, and that you can go back and review that if you, or just reprove that if you need to. You basically do everything the way that you'd hope that it would work, and it works. So remember that. If you pull back normal subgroups under a group homomorphism, you get normal subgroups. If you start with normal subgroups and you push it through a surjective group homomorphism, then you also get normal subgroups. So anyways, so we have this normality. Gi plus 1 mod n is normal in Gi mod n, and when we pull it back, what we get is we get Gi plus n is normal in Gi. So that's normality, blah, blah, blah. Okay? And furthermore, we have that this quotient here is isomorphic to this quotient by the isomorphism theorems, because n is a normal subgroup of G, and let's see here. Well, no, n is a normal subgroup of Gi, and Gi plus 1 is a normal subgroup of Gi which contains n. And that's all we need to apply the isomorphism theorem. I think that's also the first isomorphism theorem. The second one is the one where you have the intersections and the weird stuff. Well, it's not really weird. But anyways, so that's that. Alright. Also, so we have this isomorphism here from here to here, and these quotients come from here, and sigma bar is an abelian composition series, and so these are all abelian, and so these are all abelian. And so what we get is that if you go from G equals G naught all the way down to Gm, that's going to be like part of a abelian composition series because each inclusion is normal and each quotient is abelian. That's what we just proved. But then when we get down to Gm, we proved is equal to n. And then from n, we already have a composition series with abelian graded pieces. So you just stick the two together, and what you get is an abelian composition series for the overall group G. And having an abelian composition, a composition series with abelian graded pieces is equivalent to being solvable, and so G is solvable. All right, and there you go. This completes our proof.